Okay, so today we're going to be learning about the Born-Haber cycle. Now, the Born-Haber cycle is just a way to find the lattice enthalpy of an ionic salt. Enthalpy of ionic salts. Now, what that means is the enthalpy to go from Na gas plus Cl gas minus and turn that into NaCl. This is a delta H of formation, but specifically it's of a lattice because ionic salts are lattice structures. So the problem with this process is that while we can figure out enthalpies of formations experimentally, we cannot do it with a lattice because to do this, we have to dissolve the lattice in a solution, and even that alters the effects and the results of the experiment. So this is just a very multi-step Hess's law. So let's go ahead and start it out. Now, I'm going to start by writing a basic equation, but instead of doing it in the way we standardly see chemical equations like this, I'm going to change our format. So instead of using a horizontal arrow, I'm going to use a vertical arrow. So I'm going to start with sodium in its natural state, Na, solid, and I'm going to start with chlorine in its natural state, Cl, gas. Now, when I start with this, you'll notice I'm using 1/2 Cl. The reason for this is because we are doing a delta H of formation. And we have to remember that delta H of formation results in 1 mole of product, which is what we're doing. We're only making 1 mole of NaCl solid. This is our delta H of formation standard of sodium chloride. So this is a known value that we have, and we figured it out experimentally. Now what we have to do is figure out how to take our sodium chloride from solid and gas, and we have to turn those into these values that we listed up here. We need a positive sodium ion in a gaseous state and 1 positive chloride ion also in a gaseous state. So we're going to make our first change, which is actually converting the sodium into a gas. So I'm using down arrows to represent exothermic, things that release heat, and up arrows to represent endothermic, things that absorb heat. So to turn sodium from a solid to a gas, we actually need to absorb quite a bit of heat. And this is our delta H of atomization. So when we atomize just our sodium, we end up with Na gas. So that is the only change between our first one and our second one. Now, we do need sodium to become an ion, so we need to lose an electron. So once again, we're going to now remove an electron. When we remove an electron from sodium, that's called ionization energy. And you can just find that value in the periodic table. This is our first ionization energy of sodium. And when we do that, we end up with Na plus gas plus an electron plus our 1/2 Cl gas. All right, so sodium is now in the state we need it to be. So next up, we just need chlorine to both be a gas and to gain an electron. So for chlorine to be a gas alone, you'll notice the big difference here is we have no subscript. And actually, I've been making a mistake throughout this. This is Cl2, 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 and that is to dictate that it is diatomic, but we need it to be Cl1. So the way we do that is by breaking the bond in the chlorine. This is referred to as the bond energy. So to get there, and this time I'm going to draw a big horizontal line so that I have space to go down. Again, we absorb heat for this because we are breaking a bond. Bond breaking is endothermic and bond forming is exothermic. So this is bond energy. You can find that in your data table in table 11 of your data booklet. So now we have Na plus gas plus an electron plus Cl gas, and our chlorine is alone now. The next step of this is adding an electron to the chlorine. And if you look, we already have an electron in our equation, which is perfect. So chlorine readily accepts electrons. This is called electron affinity, and that is an exothermic process for chlorine. So this is going to be called our electron affinity. And I'll write these values out. Electron affinity. And that before was bond energy. So when we add those electrons to the chlorines, we have our equation now Na gas plus Cl minus also a gas. And now we're in the state that we need to be for our lattice enthalpy. So now that we're here, we have one final step to do, and that is the drop all the way the formation. Again, this is a delta H of formation. Delta H formation of a lattice, otherwise just known as delta H lattice. And these are standard values because once again, we're still making 1 mole under standard temperature and pressure. And all these down arrows are negative because they're exothermic. All the up arrows are positive because they are endothermic. So now all we have to do is combine this into an equation. So delta H of formation, our standard delta H of formation right here, that is equal to, and now I'm just going to go around this kind of circle or almost loop to get, instead of going this one big drop, I'm going to go all the way around. Because according to Hess's law, it doesn't matter how many steps you make, your starting and end product are the same, then the overall enthalpy should be the same. I'm just going to add these together. Delta H atomization plus ionization energy first for sodium plus bond energy for chlorine plus electron affinity for chlorine plus delta H lattice. So now that I have this whole equation, I can actually get real values for each of these individual ones. But before I do that, again, the whole point of this was to identify just the lattice enthalpy. So I'm going to do just a little bit of math to rearrange this. So delta H lattice is equal to delta H formation minus all these values we have. Delta H atomization plus ionization. And this is sodium again. I should write that here. Plus bond energy, chlorine, plus electron affinity, chlorine. And that is the rearranging of all this. So all I have to do now is plug in real values that I can pull from the data booklet. So after pulling these values from the data booklet and embedding them here, these are the proper values to solve for lattice enthalpy. Then all we have to do is just put that in our calculator to find that our delta H formation of the lattice of sodium chloride is equal to negative 787. I want to rewrite that. Negative 787 kilojoules per mole. And while this process does seem quite difficult and like you need to memorize a lot of things, really what this is just a step-by-step changing of variables. So we start with our sodium solid, and the first change is turning it into sodium gas. Then we take our sodium gas and change it into a sodium gas ion. Then we focus on our chlorine and we turn that into chlorine atom. So we go from a diatomic chlorine to a chlorine atom. Then we take our chlorine atom and we turn that into a chlorine ion. Then we take our whole thing and turn it into our standard NaCl. And so we have two different points that we are getting to NaCl, but one of them is our known value, our delta H of formation, and the other is our unknown, our delta H of lattice formation. And so we're going to use Hess's law. Again, we have the same starting point and ending point. We're just kind of taking a little bit more of a circuitous route to get there. Hopefully this helps. Have a great day.